All right. So let's talk a little bit about evaluating functions. So if we don't have a graph of a function, if what we have instead is just like a function formula, this is probably the most common thing we're going to see, right? So some sort of f of x equals, and then we can essentially put in any kind of function formula we want, some sort of algebra expression with x's, right? So the input variable x is what's going to be in our formula. So let's do like a relatively short polynomial type expression, maybe something like 2 times x squared minus 3x plus 1. So pretty short polynomial, nothing too wild here. This is going to be our function. So this is our function formula. So evaluating functions is just about subbing in different values for the variable. So our notation, right, is sort of f of x, f parentheses around the x. X is our input value, our input variable. And so whatever we want to put into our formula, whatever we want to put into the function, we're just going to replace the x in our parentheses here, and that's going to signal us to replace all the x's, no matter how many there are, in the formula with the same thing. So let's find a couple different things. Let's just do a couple with numbers first. So let's do f of like positive 2. Let's do f of 0. And let's do f of negative 2. So we'll do sort of a positive number, we'll do 0, and then we'll do a negative number. We'll get a little bit of a spread here. And so all we're going to do is sub these numbers into our formula. So f of, I'll color code this a little bit, right? So f of 2. So that means our x value is 2. So in the formula, everywhere there's an x, I'm going to replace it with a 2. My suggestion here is use your parentheses generously. Use a lot of parentheses. Wherever the x exists, we're just going to replace it with a 2. And then to evaluate it just becomes a little bit of an exercise in order of operations, right? So we're just going to replace, we have replaced the x with 2, with the value. And we're just going to sort of order of operations style run through and sort of calculate all this stuff. So obviously exponents first, 2 squared is going to be 4. Times the 2 out front, we'll sort of do that in a minute, minus 3 times 2 is 6, right? So minus the 6, and then we have this sort of plus 1. This is pretty fast now, right? So this is, well, 2 times 4 is 8, right? Minus 6, and then this plus 1. So if we just kind of add all these guys up, 8 minus 6 is 2, 2 and 1. Our final answer here is going to be 3. If we're thinking of this in terms of like x's and y's, so we could sort of write as a final thing, so f of 2 equals 3, right? This was our x, this was our y. If we were doing like a table, right? X values here, the f of x equals y. So this was x input was 2, and the output was 3. So if we were going to like graph that as a point, it would be at x is 2 and y is 3. Let's do these other ones a little faster. So try to keep this in frame. So how about f of 0? 0 tends to be one that's pretty fast. The temptation with 0 is to simply say you get a 0 out of it. What will happen a lot of the times, right, if you're adding or especially multiplying or dividing, you get a lot of zeros, right? Everything multiplied by 0 is a 0. 0 squared, for example, right, is going to be 0. 3 times 0 is 0. So a lot of times, whatever you're in your formula, right, wherever you have an x variable, it's just going to go to 0, and to a certain extent, whatever that term is it's connected to will probably also become 0. Obviously, that's not always going to happen. The temptation, to a certain extent, could then be to just say f of 0 is always 0. We're going to get, right, 0 minus 0, but then plus 1. So our final value here is that constant on the end, which is 1. This is going to be what we call our sort of y-intercept if we were doing graphs of this, right, where the x value is 0. That's where we are sort of crossing the y-axis, and so that would be at y value 1. If we again kind of like sum this up, f of 0 equals 1, and then in our table, right, we could say 0, and then the y value is 1. Kind of having these guys, right, feed into these pairs. That's not terrible. Let's do this negative 2. F of negative 2. Whenever there are negatives involved, of course, we have to be extra careful about our order of operations. This is going to be, right, a negative 2 squared, but then also just a regular negative 2. My negative value is inside the parentheses, right? So this is an input value. So if I do negative 2 times negative 2, that's going to get me to a positive 4. Negative 2 times negative 3 would get me positive 6. We're going to add 6. This is, of course, then, right, times the 2 in front and then sort of plus this 1. So this gets to be sort of a surprisingly big number relative to some of these other ones. So this would be what? Positive 8 plus 6 plus 1. So this gets pretty big pretty fast. Where are we going to end up? 14 and 1 is 15. So our kind of conclusion here, right, f of negative 2 is 15. And if we were sort of putting this in the table, negative 2, 15 is here. If we were trying to sort of start to make a graph of this curve, these values are a little bit random. This is probably not enough information to really make a good sketch from. We'd want to fill this in, probably use positive and negative 1 at the very least, and then maybe even some other values outside of that, just to try to see a pattern a little bit better. The second thing we can do, shift this down, is we can also sub in other expressions into a function. Get down to the bottom of this paper here. So this isn't going to necessarily give us table values, but we could take a minute and we could find f of, let's do x plus 2 and f of negative x. So we can obviously put any number we want into this, assuming it's in the domain of the function, right? Assuming we're not going to get any sort of a undefined or does not exist type value. But we can also do other algebra expressions. We can essentially input any kind of expression, not just numbers, but any kind of algebra expression into this we want. Again, provided nothing too wild happens. That's like technical math language. Nothing too wild. So let's look at what happens if we do f of x plus 2. Hopefully I didn't take up too much space. So x plus 2 going into the parentheses. So what that means is in my formula, which maybe I'll sort of write, this is where f of x will just recycle the same one we were using before, 2x squared minus 3x plus 1. F is kind of our generic go-to like function letter, but of course you could use any letter you want. It's fairly arbitrary, f for function. Usually g is sort of what comes next, g and h, because they're close by alphabetically. So this is going to be 2 times, so our input in parentheses, so not just x, but this whole quantity, x plus 2. And that's going to get squared. That means we're going to have to sort of FOIL that out and expand it. Minus 3 times, same thing, x plus 2. That's going to be some distribution, right? Distribution work. And then plus 1. What I'm going to do for this x plus 2 quantity squared, I'm just going to sort of pull that off to the side. This is going to be for us, right, sort of a FOIL, or I'm going to do it as like a box multiply. So x plus 2 squared, let's go and just do x plus 2 times quantity, x plus 2, so that's going to get me x, and x is x squared, 2 times x is 2x, 2 times x is 2x, 2 and 2 is 4. Everything here is plus, So this is going to be x squared plus 2x plus 2x plus 4. This would be kind of, in the end, x squared plus 4x plus 4, right? If I sort of combine my like terms. So, times 2, all that stuff in the parentheses, x squared plus 4x plus 4. So again, we just have this times the 2 on the outside. We're not going to do that yet. We'll sort of do that as a second step here in a minute. The next thing we're going to do, right, is distribute. So this is minus 3 times x is minus 3x. Minus 3 times plus 2 is going to be minus 6. And then this sort of plus 1 is here on the end. So what I'm going to do is just distribute everything here times 2. I could do a little bit of a combining like terms. I might just wait till the end and combine all the like terms in sort of one step at the very end. So this is going to be 2x squared. Right, trying to distribute here. 2 and 4 is 8x. 2 and 4 is regular 8 minus 3x. I just said that I wasn't going to do this yet, and yet here we are, and I'm doing it. Minus 6 and plus 1 is minus 5. Apologies for lying, I guess. And so at this stage, all we need to do is combine our like terms. So what are we left with? Well, 2x squared, sure. 8x and minus 3x, so that's going to be plus 5x. And then I've got plus 8 and minus 5 would be plus 3. So our final version here, so this was f of x plus 2. So what I get is just a new expression, right? I'm not going to expect to just end up with like a single number. If I'm not just putting a number into it, I'm sort of ending up right with a new expression. This is what it's going to look like. Quickly here at the end, I'll do this f of negative x as well. This is going a little bit long, but no reason why we can't squeeze all this in. Negative x is faster because it's just not, it doesn't have the same kind of like foiling work. What we need to watch for essentially is just a matter of when will the negative have an impact and potentially flip the sign of our different terms, and when is it just going to sort of get absorbed if, for example, it's getting squared or like raised to the 4. Oops. Speaking of squares, so sub it in, negative x here, right? So 2 times negative x squared, negative times negative is just going to be, right, a positive x squared times the 2. Negative 3 times negative x is going to be plus 3x. And then we've got plus 1. So what I get is like a very kind of minor alteration to what we had started with. 2 times x squared is just 2x squared. That's essentially the same as what we had started with in the original formula. What happens here is the negative x times the negative 3 becomes positive 3x. And then this guy is plus 1. Hey, Max. And so that's our result. That's the end of it. So that was f of negative x. And that's the plan. And that's my cat's tail. There you go.